Okay, so good afternoon. I'm here to present foundations for a Rust-like borrow checker for C. So first of all, this is the work of a master thesis by Tiago Silva. He was the master student, but he could not be here today, so I'm going to present his work. I'll give an overview of the work. The technical details will be in the paper, okay? So first, why do we care about memory safety? It will not be a surprise to anyone if I say that C is an unsafe language, a very unsafe language. And if we go to the CVEs, we can see the vast majority of them every year is about memory issues, okay? So there are several problems to solve this. One of them is, for instance, having a language that does not have the same problems that C has. That's what languages like Rust and Go do. However, even if Rust is gaining traction, C is not going anywhere so soon, so we have to deal with it somehow. So the idea of this work is, can we replicate Rust's memory safety guarantees, but over C code? Okay, so first introduce some concepts. Rust uses a borrow checker, which is a tool that enforces statically at compile time if certain properties are present in the code. Rust itself has been having several iterations of this borrow checker. So every one of these iterations are sound, so they all they do not allow wrong code, but the difference between iterations is that each one tries to have false positives, okay? So the difference between the first one and the second one will be, the second one will try to, you have Rust code that it's okay, but the borrow checker might not be able to understand that it's okay. So this is what each iteration has been doing. The work that I'm presenting is based on the non-lexical lifetimes version of the borrow checker. There's also a newer one being developed, Polonius, but this is still very recent. So we went for the more mature one that's currently being used, which is NLL. Okay, so some basics about Rust so that we understand what kind of analysis we will be doing. There will be a quiz later, so pay attention. The first thing to understand about Rust is that every read is a move, okay? So that means in that assignment, A equals B, we are moving the value of A into B. Or if you give A to a function call, we are also moving the value of A inside the function call. There's an asterisk here. If it's a type that implements copy trait, it's not a move, it's instead a copy. But for copies, there's no problem. The problem is when we have pointers, references, okay? So that's putting that aside. Let's consider only moves. And one key idea is that after a move, the original value is no longer valid. So when I do B equals A is no longer valid, okay? But sometimes I don't want to move. I just want to borrow the value. That's where this concept of borrow comes from. In Rust, you have syntax for this. The ampersand is a simple borrow. And you have also a mutable borrow. If you want to let the variable change or mutate the value. We can condense what's happening on this table. So, for instance, if we borrow the value to another variable, every variable can read, okay, and you can have several of them, and you can reborrow. Your borrowed value can be reborrowed to another variable, but you cannot change it. Okay? Until all the borrows have finished used, there's no changes that can be made to the code. Okay? when you do a mutable borrow, you are giving permission to write, and only the owner of that mutable borrow can change the code and read it, okay? So that's how we can ensure some memory safety concerns. So all those rules have the following consequences. So values must be initialized before they are used. No uninitialized values are not allowed. You cannot move a value twice, because if you move it once, it becomes invalid, so you cannot move it again. If a value is borrowed, you cannot move it, okay? Only after all the uses of the borrow. If it's mutably borrowed, you cannot access. And if it's borrowed, you cannot mutate it. So this derives from the previous rules that I've shown. Okay. So quiz time. This Rust code has an error. So I'll give you 15 seconds. If someone discovers the problem, please tell me. Okay.
Line 11, cannot mutate foo whilst mutably borrowed by P. Whilst borrowed by P.
Wrong, sorry. Foo equals 4, it's okay, because you borrow foo into P, right? And then you use it. But P is no longer used in that branch, right? Because bar overwrites P. So P is no longer being, you are not, so the problem is not the 11. Any other suggestion? Okay, that one in yellow, who was first? Exactly. So that's the answer. The thing is, the first borrow inside the if, P after the last use of P is on line 10. Because it's rewritten in 13, P disappears after 10. The borrow ends there. But after the if, P is still being used on line 17. So you cannot mutate while it will be used. So this is the kind of analysis that the borrow checker of Rust does, okay? And it outputs error messages like this. And our objective will be having messages like this, but for C code, okay? How does Rust does it? So Rust has a couple of internal representations. One of them is MIR, which is basically a CFG. And it's over this CFG that this analysis is done. So now I'll introduce Coral, which is the tool you developed for this work, where we replicate this behavior, but for C. So in Rust, you have special syntax for specifying what is a borrow and a mutable borrow. We don't want to change C. We want to use C exactly as it is. And so instead of having special syntax for the borrows, we are using the types of the variables to distinguish between what is a borrow and what is a mutable borrow. Okay, so for instance, we have this code. That was the previous example. On the right, you have C code equivalent to that Rust code, and we want to detect the same kind of problem. How are we doing that? So we are using a source compiler, this Clava, which was developed in our lab. And one special thing about this compiler is that we can extend it without modifying it. We can write compiler passes in TypeScript that are interpreted by this compiler. And Coral is basically a TypeScript, JavaScript library that was implemented that will be executed by this compiler. So there are two phases in this compiler, in this library. The first one is normalization or canonicalization of C code. So in order for the analysis to be simpler, to simplify the analysis, we first do some automatic transformations on the C codes, okay? For that, we are using previous work. It is another library for Clava that does that kind of normalization. Then we build the CFG, similar to what happens in MIR, and it performs the same analysis with the same restrictions and inference of lifetimes. Okay, so after all that, this is what we are obtaining. So if we give that code to Coral, it will output a very similar message as the one that Rust obtains. It uses the same three-point narrative. It's how they call this format, this message format. And most of this work, but again, this was done during a master thesis. And just to explain, in Portugal, a master student has around 4 or 5 months to dedicate to the masters. And most of the work was understanding how the Rust borrow checker works. It was not easy because although there are a lot of information, it's scattered in many RFCs, in many documents. We also had to check the Rust source code to understand sometimes what was going on. So one of the main contributions of this work is gathering all that information, and that's why this is called foundations for a borrow checker. But even with that, we could implement some of these checks, and I can say that we have already, after this, we continued the work, and we have submitted an extension to the text journal where we have already been able to implement most of these points, and we will continue to work on this. Okay.
Thank you so much for a great talk. So I have actually 2 questions. One is that why didn't you do in the LLVMIL level? Why did you do that in the C source code level?
Okay, so for several reasons. One of them is to avoid being tied to a specific compiler. So because we do this at the source level, then we can just do the check and give the source code to GCC, CLang. So that was one of the reasons.
And my second question is that I believe that the power of the Rust type system license is support for unsafe features like interior mutability. So do you have a plan to support interior mutability that is understood in some semantic types in Rust?
Sorry, what was the term that you said?
So interior mutability or unsafe features Rust is, I think, one of the most important features in each type system. So do you have a plan to support that?
Okay, so first, this first work, we were trying to follow Rust rules very closely, but in next work that we did, we tried to make it more native to C. Okay, so the objective is trying to be as close as C as possible. For instance, in Rust you don't have nulls, but in C you have nulls. If you forbid nulls in C, you will not accept any code. So we are thinking about techniques to handle that. But of course, one of the things that we want to support is boxes, okay, to handle the dynamically located memory, and of course arrays and slices.
Okay, thanks for a nice talk. I've a question regarding how you actually translate C programs into the typeset programs like you presented. Can you do this automatically or it has to be done manually?
Okay, so for this work, we were requiring some manual changes, but right now we are, for instance, we are no longer asking people to put the restrict. We'll try to infer if it's needed or not, if it's a mutable borrow or not. Also, there's a pragma-based language to annotate lifetimes, but we can also infer most of them. But if the tool cannot automatically infer, you can go there and indicate what are the lifetimes of the function. So, but the idea is trying to automate as much as possible.
And in your extension, you also mentioned the possibility to use heap right? So how generalized is that? Because you can do whatever crazy stuffs there, right?
Yeah, so that's an open question. I can check. This is our current progress, so that will be the next.
As I understand it, to do some of the fancier array and slice memory safety things that Rust does, it basically just like calls into unsafe and then does whatever and provinces it's safe. So would you try to infer that for C? Like I'm curious about the arrays and slices point, really.
If I could understand correctly, you're asking the reason for slices? No.
Like Rust, as I understand it, to make things like array.split or whatever that like gives you two chunks of memory that like guaranteed are not alias to each other, like it does some unsafe operation and then just hands you back two pointers and it promises that they're safe. And so I'm wondering how you would do this in C.
It's not done yet. We have some ideas of how to implement it. So the idea of slices is also so you don't... if you give an array without slices, you are basically borrowing the entire array. So the idea of slices is just to limit what you are borrowing, right? As I said, we already have ideas for this. Let's see in future work what we can do about this. But there's plenty of stuff right there. Unfortunately, it's the students who know the technical details about this, but there are planned solutions at least. Okay.